that was very exciting.
Okay.
And then that's just when it started.
Okay. And you were doing this during the university, and then you stayed in the university doing the research?
Yeah, it was just throughout different courses and classes at university. I tended to focus on physics. So if we had like this was media technology, a master's program. So we actually had a lot of classes about 3D graphics, and we actually also had one on simulation. And whenever I got a chance, I just did something simulation. Even if it was a rendering class, I did something simulated it, and then also rendered it just to squeeze it in. So there was a lot of that during university. And then at the final semester when we did this master's thesis, I teamed up with another student, and we made our own rigid body simulator
Nice.
that's thesis.
How much work was it?
That was 6 months. I'd been doing a bunch of work before that, so but it was a pretty good amount of time, I think, full time, 6 months. It was not a great simulator, but it worked. Um, so that also sparked the beginning of this company that we formed
Yeah,
afterwards.
yeah. Uh, Rigid body. I think we should paint a picture for everybody who is listening. There will be people that are listening that have computer programming experience, but not necessarily physics related. Can you do a bit of an overview? What would be the rigid body and what would be the simulation? And we can even go further into like what is a physics engine? What's it doing?
So nowadays it's a bit more complex, but back then in the 90s, uh, if a game had any type of simulation, it was all only rigid body. Um, and rigid body physics is basically what it sounds like. Everything is rigid. So there's nothing flexing, there's no cloth, there's no deformable, there's no water or smoke or anything. Whatever you simulate is just something that is a rigid object colliding and resting on top of other rigid bodies. They can also usually be connected by joints. So you can have two things connected by a hinge joint or a ball joint and things like that. And not long afterwards, people started using this, of course, to connect limbs of a character, and then you could have, and that's how the ragdoll physics was formed. But yeah, that's basically what rigid body physics is. It's still the dominant when people talk about physics in games. It's still rigid body physics they usually mean, even though now we have a very uh, advanced simulation of cloth, fluids, smoke, deformables in games.
Okay, we'll get to that
Yeah,
based on your projects. So you finished the university and you formed a Mekon uh,
Mecon
research.
Research was the name, and yeah, it started around this thesis that we did at university, but I don't think any of that code really survived that long into that project. Um, we rewrote all of it. The the simulator we did at university was more academic. It was more like a mathematical um, linear equation solver that solved things very accurately. It has the advantage of giving very nice results if you feed it good input. But it also has the downside that if you feed it not so nice input, it tends to just explode and everything flies all over the place. Um, it's also not very fast. The performance is very unpredictable. So if you have like 10 bodies, it works fine. If you had like 100 or 1,000 bodies, uh, the scale of performance tends to not scale so well with the number of contacts. So it's kind of like a quadratic scale of the thing, and it's just not acceptable for games. So we had to come up with something something else, and that's when we also discovered these iterative methods for solving these equations. So we started using that, and that's still what people are using, I would say, for rigid body physics.
Okay. Maybe we can also paint a picture. So I learned when I was doing this physics simulations that the issue is when you're doing the simulation, you can have an error in your computations. And because you're doing this like frame by frame, these errors can compound. So the stability of the simulation is quite important, right? Because you need to
Right.
think about it like in a long spans of time.
Yeah.
And there are two large categories, right? There's a physics simulation that wants to be like super accurate, but time is not constrained. And there's the game game physics where you are very constrained about the time and you don't want to just compute, let's say, a couple of seconds and you have, let's say, 1 day to do it. You need to compute it now in like a frame because you need to render it immediately, right?
Yeah.
So these are the, I think, at least in my mind, there are two like separate categories. Is this correct? More or less?
Yeah. I think what's happening now and has been going on for a while is that these two are kind of merging.
Okay.
That the methods we're using in games and have been using in games um, are approaching the more academic or like the research oriented simulation, because they usually give the same result. So if you just decrease the time step, you can actually get the same result, and it's always nice when things go fast. So sometimes you can even get better accuracy with these in the same amount of computation. You can actually get really nice results with these simpler iterative methods if you just lower the time step enough to make it
Okay.
more to improve the accuracy. So they're not like two different worlds.
Okay.
It's actually closer than you might think.
Okay. Can we spend a bit of time before we go into like what Mikon did and then further to talk about time steps, fixed time step versus non-fixed, and then when you say iterative methods, what do you mean by that
Mhm.
exactly? So to paint the picture.
Sure. So physics for games, usually, well, always, I would say, solved in time steps. Uh, and say you have like a 60 hertz update of the screen, you can tick the physics also at 60 hertz, or you can tick it faster or slower. It's a little different depending on the game, but you always do it in discrete steps. Um, and for most simulators, it's pretty important to keep this time step fixed so that you always um, take the same amount of time forward every frame. And the frame rate is not always fixed in the game, of course. So that can cause some trouble because you want to keep the physics at a fixed rate, but not necessarily the rendering. So that's when you're going to have to start interpolating the result. Um, and these are not really tied to the iterative solver. Um, so you take the physics at one rate, and then um, maybe we should break down the physics, what the physics engine
Yeah.
does to
Yeah.
understand the iterative solver. So usually in the physics engine, you have a couple of different phases, where the first one is to do collision detection. The most complicated part in the physics engine is usually the contacts when things collide. The joints are sort of easier. They're always the same in between two bodies. But for the contacts, we need to first find uh, what are all the overlapping or potentially overlapping objects. So that is done. You see, usually you have like a bounding box around each object, and then you find overlaps between these bounding boxes. It's called a broad face collision detection. Then you get a list of pairs, and then you go through over these pairs, and you do a more detailed thing where you find not only the point where they overlap or the closest point, but actually a number of points that in most physics engines these form um, a convex patch between these objects. So this is what you send to the solver. And then the solver figures out the next dynamic state of the simulation. So the input to the solver is like, where are all the objects? What are their velocities, their mass properties, and stuff like that. And then you also send these contact patches or contact points. And then it figures out how things can move, because if you don't have any constraints, bodies just tend to move the way they moved. But if you introduce these contacts, you can say, okay, it wants to move like this, but there's a contact in between, so it has to respond to that somehow. And this may sound pretty complicated, and if you formulate this mathematically, it is pretty complicated, because it's not just a system of linear equations, because it actually also has the property that a contact can only push on objects. It cannot pull. So it's not like a linear thing where you just compute this value, but you also have the constraint that it has to be positive. It can only push things apart. But it's actually not that complicated using an iterative method. So instead of seeing this as this big mathematical problem, it's called a linear complementarity problem. Instead of doing that and solving it mathematically, what we do, you just go around at every contact, push it a little bit, like solve every contact separately. And if we do this over and over and over again, we actually end up with a thing that converges towards the correct state. But it can take a number of iterations to do this, and that is basically the method of solving this iteratively.
Okay.
And the implementation is also much more much simpler than doing the mathematically correct thing.
Okay.
So you just basically just a loop over contacts, solve each contact as if that was the only contact, and then you just move on to the next.
Yeah. So instead of looking at all of the objects at once and figuring out where each one would be, you think you localize this and you look at, okay, here's one contact point. These are the objects that are touching, how they should go away, and then you solve
Exactly.
them one by one. Okay.
Yep.
Okay. Okay. Regarding the time step, I think I've heard it that you can have a stable simulation with a variable time step. Is this correct? But it's not common.
It's not common, and it's even though you can get there, it's very few people are doing it, because the reason is that if you give it well-formed input, that can certainly work. But if you normally this iterative method of solving it, you go over these contacts and other constraints a number of times, and usually you could solve it until every constraint is satisfied, but that's going to take a long time. So what you do is you typically cap that at the number of iterations. In many games, it could be like 4, 6, 8 iterations. And then you just say, okay, enough. There's going to be a small error. We'll fix it next frame. So you get these errors that you then compensate for the next frame. And this error is also going to scale by the time step. So the error you got from, say, the previous frames or the accumulation of all the previous frames, you then want to fix afterwards. And if you get varying time steps, that's going to over or under compensate depending on whether the current time step is longer or shorter than the average of the previous ones. So you can get into these shaking and self-oscillation and things like that.
Okay.
There are ways to try and compensate for this, but it's never going to be perfect, because if you vary the time step a lot between every frame, that's really hard to work with.
Okay. So basically, by having a fixed time step, you also are locking the error to some sort of like order of magnitude, like a size, and then you can reason about what was the error in a much easier way than if you had the variable one.
Yeah, you're not really locking the error or clamping the error to a certain
Yeah,
range. It's more that if you had an error from a previous frame and you want to fix it in the next, you typically want to know, um, in order to reason about how to fix it in a certain amount of time, or give, you can almost see this as like a spring. Say you have two objects and they collide and there's a contact in between them, but the solver doesn't manage to fully resolve that. They're going to still move towards each other a little bit, ending up in penetration. And
yeah,
then that, you want to fix that amount of penetration, and you can only do that. You can see that as kind of a spring damper. So you have like a little spring trying to push it out.
yeah. Okay,
Um, and reasoning about how stiff that spring should be to make it look nice and
okay,
smooth is really hard if you don't know the time step.
okay,
Um,
okay.
yeah,
All right. So with this as a foundation, now Mekon research. What was the idea for the institute? Was this like research institute or was this like a company? What?
research was just a part of the name. It was just a
Okay.
company. It was
Okay. So what
not.
was the company goal? Uh, what was the product? What was the vision?
Um, yeah, so we had like the Mekon SDK was just it was a physics engine that was the intention to just plug it into the game engine. You feed it your objects, it takes care of the calculations of the physics, and then you can get the result back, like just like what you have today with PhysX or Bullet or Havoc or something like that. Um, when this came out, physics was not widely used in games. So this was kind of a new thing. We had a couple of competitors. One was Math Engine.
Okay.
I don't know if anyone remembers that. Um, and then there was Havoc. That was pretty new at the time. Um, there also after a couple of years they've been running, there was also a new one called Novadex that started to show up, which later became PhysX. Um, but physics engines was a pretty new thing back then. So I think we were a little bit naive to think that we could just come right out of a university and make a product and have people be excited. It's really hard to sell middleware to game developers if you're not solving a problem. Like this is
Yeah.
something I thought a lot about. Like if you want to sell new technology as middleware to a studio, that's a really tough sell. Like that they're there with their games, their deadlines, and there comes some other guy. Hey, wait, maybe you want to add all these bunch of features with all their problems, and it's a hard sell. And since physics wasn't usually planned in games, we tried to sell them a problem rather than a solution, which is hard. So the company didn't do that well. I must say it was tough.
Okay.
It was a little early for physics engines, I think.
What, how does the situation change over time? Now it's like you have a Unity and Unreal, and Unity ran uses now PhysX for the majority, but for 2D uses Box 2D. And now with the new dot stack, I recently talked to Aras from Unity, and he explained that there
Mhm.
are actually four engines in use, like in terms of physics. It's like how does this market look like now? Is this like everything locked as far as you could tell? Like you have two big engines, they use
Yeah,
this. It's
I don't follow it really closely actually, since I always built my own engines. I'm not a user of uh, Unity or Unreal, so I can't really say. I know it's pretty complicated these days. Um, yeah, I can't really say anything about it because I haven't used that part. I also know some people writing their own physics engines for using
okay.
in Unreal. So yeah, it's a little complicated. One would have thought that it would have stabilized by now, but it's almost the opposite. It's getting more and more complex.
So for the Mekon research, you were developing the physics engine, and trying to sell it to game studios, right?
Yeah.
For how many years?
We started 2001, I think, and we ran it for 4 years, I think. We did get a couple of clients. It was the only big one was Duke Nukem Forever that we signed in, was it 2004 maybe? And that was a good one because they never, I mean, it went on forever, and then it was a highly anticipated game at the time. So we could use that as, as like an exciting customer for a long time. But other than that, there were a few smaller games using it. We had some venture capital. The company never did well financially, I would say. Um, and then eventually we got acquired by this American company, Aegea, in that was in 2005. Yeah,
Aegea?
Aegea. That was, yeah. No one remembers that. They did the physics hardware accelerator. Some people
Oh,
remember that. It was back in, yeah, it was 20 years ago. Everyone saw the success of the graphics accelerator, and Aegea had this idea, like, we want to do the same thing, but for physics. So you
yeah.
buy an extra hardware, plug it into your PC, you get awesome physics. Um, that didn't really work out.
Yeah, yeah.
No one has a physics accelerator nowadays. Um, so they bought Novadex, this company in Switzerland that was a competitor to us. And then just a year later, I think they also bought Mecon, and we tried to incorporate some of our stuff into that, even though most of it was actually Novodex's stuff. Um, but that's kind of where the Mecon journey ended. So we got
Okay.
sucked up into the Aegea and trying to do hardware physics together with the guys in Switzerland.
Okay. This is this is when you were flying to Zurich.
Yes, I was flying back and forth
Yeah.
Sweden and Switzerland for a while, and it was a very rewarding thing because there was so many smart people there. It was fantastic. Um, Most of them are still on the physics team, actually,
Oh,
20 years later.
that's a great
Um,
sign. That's a great sign.
yeah, yeah. Um, so 2005. I don't know when Aegea eventually got bought out by NVIDIA. I think it was maybe in 2008 or 9 or something like that.
Okay.
And then this office in Zurich got turned into an NVIDIA office for doing the physics
Okay.
SDK, or continuing the work on the physics SDK. But instead of doing it on a dedicated hardware, you do it as
Yeah.
part of on the GPU instead.
Yeah.
And I
Can
think
we?
the whole idea with a separate accelerator card for physics, it wasn't that great to begin with,
Yeah.
because because a GP, I don't think they maybe anticipated the way GPUs were going towards more general compute,
Yeah.
because the physics accelerator was basically also just, I mean, it's all just a number cruncher, like different cores operating with their local memories, and then GPUs going also exactly that direction. It was kind of
Yeah.
merging. There was also a lot of problems with Aegea and physics, and this thing I talked about solving a problem. It was even bigger when trying to do hardware physics. Like, imagine coming to a game studio
Yeah.
on a timeline and asking them to do extra content and extra features for these very, very few people that actually buys this hardware.
Yeah.
Um,
And then tell
we had
your
to pay them, of course, to do that, but it was, yeah, it was very messy, and
and then
I learned a lot about making products from that. Like, don't try to make a problem. Try to make something that solves a problem instead.
Then imagine Game Studio, like not only you sell them this issue, but they also need to go to their customers, the gamers, and tell them, guys, you should really buy additional piece of hardware to run
Yeah,
our game. It's like,
yeah, and of course, no one could require that, so they had to make the game fully playable without
yeah,
the physics accelerator.
yeah.
But there were many other problems also with the GM, like the amount of speed up that you actually got wasn't. It didn't really motivate buying extra hard. And this was also around the time where PCs started to get extra cores. Up until now, everything was single core PC, but around that time, these dual core machines started showing up. And then instead of running physics on a PPU, like the physics processing unit, you could just running it on a separate core, and that was fine. So, so it was a lot of bad timing, and yeah, I don't know.
Uh, can we talk a little bit about how hardware is used in terms of CPU, GPU?
Mhm.
How much of the physics engine work can you do multi-threaded? I know that some of your recent work was
Yeah,
in this area, but so that like because I heard about this PPU idea and it was that it was in the past,
yeah.
but generally speaking, now we have CPUs and GPUs, and CPUs can do a lot of work that is fast. And but they have couple of cores, and we have GPU that are highly parallelizable for things like matrix multiplication. And how does the physics computation fits in this mindset?
So I think what most people do, and what I always do also, is to run the physics only on the CPU. Um, you can run. There's some things that could work well on a GPU, like particles. For instance, if you want to do smoke or fluid simulation, that could work. But for rigid body physics in particular, um, it's not very well suited for the GPU. Not from a technical perspective, or like a hardware perspective. It runs fine uh, on a GPU, and that there are people who have done that. Um, but from a gameplay and game engine perspective, uh, having the physics run on the GPU is not usually not a great idea, because you want the result of the physics. The gameplay usually depend a lot on the output from the physics. So you do want the result immediately. And usually when you do something on the GPU, and you can synchronize the buffers and send it, but the GPU is never in sync with the CPU, or it could be, but it's usually a bad idea because of all these stalls. Um, so if you want to do physics on the GPU, you kind of have to push gameplay to the GPU also, because you simulate a bunch of bodies, you see these two overlap or these two are close to each other, and you want to do a rate cast here and there, and then you want to take that result and maybe spawn an enemy or something. Or in my case, in Teardown, two things collide and there's a strong enough force, I want to split up the objects, create new objects, and blah blah blah. And
Yeah.
it's awfully complicated to do all that on the GPU. So since you have to put gameplay code on the CPU, it's just not really an option to do to do the physics on the GPU. And there are some parts of the physics pipeline, like we talked about before, this broad phase collision detection for checking overlapping pairs, that can be very efficiently implemented on the GPU. Also the near phase, which is 100% parallelizable to check these pairs and generate lists of contact points or patches. Also very well suited for parallelization at a massive scale. The solver is harder, because when you um, it actually typically does not parallelize well at all. Not the method. There are actually two ways to do it. One is called Gauss-Seidel, which is the one I described earlier. You just solve each contact separately. And then after solving the first one, you have adjusted the velocities of those two bodies, and then you solve the second one, taking into account the result of the first one. So it's kind of a serial operation to solve them one by one. There is one called Jacobi, in which you solve all of them independently and then try to work out the result afterwards, which also works, but it converges much, much slower. So you need a lot more iterations. And usually, at least on the CPU, it's not worth it to do it in parallel because you need to do so many more iterations for it to converge. But there are ways to go around it. There are one classical way when talking about parallelizing the solver, and that is to break it up into simulation islands. So say you have a ragdoll over here with, say, I don't know, 12, 15 joints. And then you have a ragdoll 20 meters over there simulating bouncing off the ground. Those two never touch each other or interact with each other. So you could solve them on different threads. And it's going to be fine because they never change the same body, so to speak. And people have been doing that for a long time. That's also what we do in Teardown. The problem, of course, especially in Teardown, I would say, is that it tends to be large piles of rubble. and these large piles are going to end up in the same simulation island. So there's not a whole lot to break up. And yeah, and that's what I've been focusing on very recently. And it's not an invention of mine. It's people have been doing this for a few years now, where they try to break up having a large pile of rubble, lots of contacts. There are ways to classify or break this problem up into different passes. So if you imagine say you have 10 objects resting in a pile, you can find pairs of objects, which is fine to solve in parallel.
Yeah.
But then you're going to have to do another pass to tie together the ones that didn't fit in the first pass. So you can imagine in a large pile, you're going to end up with a lot of these passes to cover all of it. And you're also going to mess a little bit with the order in which they're solved, which can also have problems. But that it's called graph coloring, this problem of trying to break up this. You can see it as a contact graph where the contact points are kind of links between these nodes, which are the bodies, and then you're trying to colorize the things that can be solved in parallel. So that's what I've been doing for the new project.
Okay. This is very specific in terms of using this as a general purpose mechanism by default in a physics engine, in game engine like Unity. It's very difficult to probably justify the complexity to use just for any physics.
Yeah, you
solving.
would need to implement the physics engine, I think, for
Yeah.
that to make any sense. You can't really modify an existing physics engine to use this unless you replace the whole solver. And it's unfortunately it's a pretty complicated thing. It was more complicated than I was hoping to make that and get it efficient. And that ties into just multi-threading and how to synchronize threads, because as you can